Welcome to my continuing series of videos where I read a paper out loud. This is something I do during the camera ready process to help me find last minute typos. About 1,000 people are watching these each time I do it, so some people are finding it useful. Maybe you have trouble reading yourself. If so, happy to do it, and it helps me find typos and forces me to do this more consistently. Evaluation examples are not equally informative. How should that change NLP leaderboards? Abstract. Leaderboards are widely used in NLP and push the field forward. While leaderboards are a straightforward ranking of NLP models, this simplicity can mask nuances in evaluation, items, examples, and subjects, NLP models. Rather than replace leaderboards, we advocate a reimagining so that they can better highlight if and when progress is made. Building on educational testing, we create a Bayesian leaderboard model where latent subject skill and latent item difficulty predict correct responses. Using this model, we analyze the ranking reliability of leaderboards. Afterwards, we show the model can guide what to annotate, identify annotation errors, detect overfitting, and identify informative examples. We conclude with recommendations for future benchmark tasks. End of abstract. Hello, Mr. Train. Section 1. Leaderboards are shiny. Leaderboard evaluations, for better or worse, are the de facto standard method for measuring progress in question answering, and in many NLP tasks. An unfortunate side effect of leaderboard popularity is soda chasing, often at the expense of carefully inspecting data and models. For example, the same superhuman models that top question answering leaderboards often fail spectacularly by learning non-generalizable statistical patterns. Finally, focusing solely on metrics conflates progress on a specific task with progress on real-world NLP problems behind the task. Plainly, focusing on headline soda numbers provides limited value for scientific progress absent insight into what drives them and where they fail. Figure 1. Difficulty and ability discriminating leaderboards infer the difficulty, discriminativeness, and feasibility of examples. Negative discriminability suggests an annotation error. For example, the question with most negative discriminability asks, why did demand for rentals decrease, when the answer is demand for higher quality housing. In this work, we take leaderboards as they are and imagine how they might better support research. Leaderboards establish differences between models on a fixed task. Hence, leaderboards should enable and encourage the comparison of models and inspection of examples. And leaderboards should also reveal when they have outlived their usefulness. To help focus attention on examples and models of interest, we propose difficulty and ability discriminating leaderboards that explicitly model both tasks and submissions jointly, rather than either in isolation. Difficulty and ability discriminating leaderboards, DAD for short. DAD's underlying model is based on item response theory, a widely used alternative in educational testing to example summary statistics. DAD can explicitly identify the difficulty and the discriminability of items, which in turn can lead to a more nuanced ranking of models, identifying poor items, and better understanding of a dataset and task. Throughout the paper, we use the question answering benchmark Squad 2.0. For example, DAD can identify questions that are challenging to models and questions that are wrong, incorrectly annotated. In addition to better understanding datasets, it is also helpful for efficiently selecting evaluation to annotate. We conclude with recommendations for future leaderboards and discuss where IRT and NLP can go next. Section 2, a generative story for leaderboards. Leaderboards are a product of the metrics, evaluation data, and subjects, human or machine. For concreteness, let's assume that we have a question answering task and two subjects, Ken, who is good at trivia, and Bert, who is not. In the simplest IRT models, each subject J has a random variable theta J corresponding to their skill. Ken's is big, Bert's is small. But you cannot know that until you start asking them questions of varying difficulty, beta. Harder questions have a higher difficulty. What is the airspeed of an unladen swallow? Then easy ones. Who is buried in Grant's tomb? The bigger the margin between a subject's skill, theta J, and an item's difficulty, beta I, theta J minus beta I, the more likely that subject J responds correctly. Probability of item I subject J response of IJ equals 1. This is the simplest IRT model, which we call IRT base. Figure 2. A DAD leaderboard uses IRT to jointly infer item difficulty beta I, discriminability gamma I, and feasibility lambda I, and subject skill theta j. These predict the likelihood of a correct response Rij. Generally, given n test items, x1 to xn, and m subjects, s1 to sm, where each subject responds to every item, we want to estimate subject skills and item difficulties. To discover the random values that best explain the data, we turn to probabilistic inference. Two additional random variables further improve DAD: discriminability gamma I and feasibility lambda I. We first consider discriminability and the margin between a question's difficulty beta I and a subject skill theta j. A discriminative question is challenging, but can still be answered correctly by a strong subject. If Kin's ability is greater than most items' difficulty, theta j minus beta I is large, item discriminability multiplies this gap by gamma I in a model called IRT disk. Questions with low gamma I are low quality. They have annotation error or do not. Another way of capturing poor quality questions is a feasibility lambda I. For example, if the question, "Who was the first president?" has the answer Rajendra Prasad, the question has an unstated, implicit assumption that subjects must guess what country or company the question is about. In the model IRT fees, if a large fraction of subjects all get an item wrong, everyone's probability of getting the item right is capped at lambda I. In NLP terms, 1 minus lambda corresponds to the prevalence of annotation errors that lead to unsolvable items. Having introduced all of the constituent elements of the model, we can now present the full generative model. For each subject j, draw skill theta j from a normal distribution with parameters mu theta, tau theta. Draw difficulty beta I from a normal distribution with parameters mu beta and tau beta. Draw discriminability gamma I from a normal distribution parameterized by mu gamma, tau gamma. Lambda I, the feasibility, from a uniform distribution between 0 and 1. Then draw a subject response on item j, or ij, from a probability distribution where the probability of getting the answer right is lambda I over the quantity 1 plus the exponential of quantity negative gamma I times theta j minus beta I. For IRT base, gamma I and lambda I are fixed to 1, while for IRT disk, only lambda I is fixed. The means, mu theta, mu beta, mu gamma, are drawn from a normal distribution with mean 0 and high variance, and the taus are drawn from a gamma 1, 1 prior, as in Lalor et al. 2019 and recommended by Natasan et al. 2016. Okay, the next page. Because it is difficult to completely codify skill and difficulty into a single number, we can rewrite the exponent in equation 1 as a sum over negative gamma I times quantity sum over k theta jk minus beta ik, where each dimension captures the interaction between an item's difficulty and a subject's skill. For example, perhaps Bert could better exploit artifacts in one dimension. Their skill theta k equals 5 is high, but everywhere else is low, while Ken might not know much about a particular topic like potent potables. Theta k equals 2 is low, but everywhere else is high. We call this model IRT-VEC. Multi-dimensional IRT models could, in addition to better modeling difficulty, also cluster items for interpretation. We briefly experiment with this, but leave more to future work. Section 2.1. Examples are not equally useful. IRT's fundamental assumption is that not all items and subjects are equal. This explains why leaderboards can fail while having normal-looking accuracies. As a thought experiment, consider a dataset that is 1/3 easy, 1/3 medium difficulty, and 1/3 hard. Suppose that Ken has skill theta k equals 4, while Bert has skill theta b equals 2. A standard leaderboard would say that Ken has higher accuracy than Bert. But suppose there's a new subject that wants to challenge Ken. They are not going to reliably dethrone Ken until their skill theta c is greater than 6. This is a more mathematical formulation of the easy and hard dataset splits and question answering. In IRT fees, this recapitulates the observation of Boygraber and Böschinger that annotation error can hinder effective leaderboards. DAD helps systematize these observations and diagnose dataset issues. Section 2.2 Inference. To estimate the latent parameters of our model, we use mean field variational inference. In variational inference, we propose a distribution over the latent variables that approximates the true but intractable posterior. We then minimize the Kale divergence between these distributions, equivalent to maximizing the evidence lower bound, elbow, with respect to the variational parameters. In our case, the variational distribution Q is a mean field distribution, which means it factorizes over each of the latent variables. The product is over the n times n subject item pairs. Specifically, for our latent variables, beta and gamma, the associated variational distributions are of the form of a normal distribution, parameterized by u and t. Recall that in the generative distribution, each latent z is drawn from itself a normal distribution whose parameters are also latent variables. For these variables, we also use a normal distribution for the means and a gamma distribution for the variances. We optimize the elbow with respect to all of the variational parameters using Atom. With Dad's leaderboard IRT model introduced, we next discuss how leaderboard subjects are statistically compared and alternative methods such as using IRT parameters to evaluate whether two models are truly different. Section 3. Ranking and comparing subjects. Fundamentally, the objective of comparative evaluations like leaderboards is to decide whether Model A is better than Model B. A thread of NLP has rightfully advocated for adding rigor to these decisions using statistics, where the objective is to infer a true score t from the observed test score equals t plus e, given a measurement error e, uniform across subjects. However, in educational testing, a field measuring skill and knowledge in humans, IRT is a primary measurement instrument. A major motivation for IRT is that subjects of different skill have different errors. IRT explicitly accounts for the bandwidth fidelity dilemma. Items can either accurately measure narrow ability range, fidelity, or inaccurately measure large ability ranges, bandwidth. This section and the next contrast methods for identifying the best model and advocate for IRT. Implicit in nearly all leaderboard evaluations is ranking models by statistics such as the average accuracy. As we show in Section 4, naive rankings are noisier than IRT rankings. Section 4. IRT for leaderboards. Leaderboards should 1. Reliably and efficiently rank better models ahead of worse models. 2. Guide inspection of items and subjects. The first ameliorates the unavoidable randomness of finite evaluations, while the second enables error analysis and model probing. First, we verify that IRT models accurately predict the responses of subjects. Next, a ranking stability analysis shows that IRT has modestly better reliability than classical rankings. Lastly, using IRT to actively sample items for annotation yields rankings with better correlation to complete test data. Section 4.1. Why a linear model baseline? At first blush, the differences between IRT and logistic regression are minimal, but we include the comparison to address natural questions from the NLP community. 1. Do the idiosyncrasies of the IRT formulation hurt accuracy? 2. Should we add features to better understand phenomena in the questions? And 3. Why not use deep models? The next section argues that both IRT and logistic regression are accurate, even without laboriously engineered task-specific features, and that adding obvious features such as item words, e.g. questions, only minimally improves the accuracy. We explicitly omit less interpretable deep models since our goal is to make leaderboards more interpretable. Just as educational testing researchers validate IRT models by seeing if they predict subject responses correctly, we validate whether DAD predicts whether squad models get questions right. We compare against a logistic regression linear model implemented with Vopal Wabbit. Since integrating handcrafted features is easy, we incorporate features derived from subject IDs, item IDs, functions of the squad question, answer and title, and IRT parameter. As in IRT, logistic regression predicts whether a subject correctly responds to an item. Later, we discuss ways to integrate more features into IRT. Experiments are on the Squad 2.0 leaderboard. Development data are publicly available, and organizers provide test set responses. There are 161 development subjects, 115 test subjects, and 1,873 items. 1.9 million total pairs. Experiments that do not need test responses use all development subjects. Those that do not use the smaller test subset. Following prior work, we evaluate IRT in linear models by holding out 10% of responses and computing classification metrics. In Squad, predicting whether a response is correct is an imbalanced classification problem. Thus, we use ROC-AUC, macro F1, and accuracy. Section 4.2.3, IRT response prediction is accurate. IRT models that incorporate more priors into the generative story should be better, but are they? We compare 4 IRT models: IRT base, IRT disk, IRT fees, and IRT vec. The more sophisticated models are better and all improve over the linear model and correlate well with each other. To be clear, while higher accuracy than the linear model is good, our goal is to validate that IRT models are accurate. Later, we inspect model errors and identify annotation. Section 4.2.4, what model features are predictive? Integrating additional features into Bayesian models is not trivial, so we instead use the flexibility of linear models to identify useful features. Our leave one out ablation compares features. The top ablations both use IRT features, further validating IRT parameters. The subject and item identifier features are also strongly predictive, but item is the stronger of the two. Text-based features are weaker, but this suggests future work to better integrate them into IRT models. Ranking with IRT, section 4.3. Leaderboards should produce reliable subject rankings. Can DAD rank systems even with a tiny test set? Thus, we compare the correlation both of traditional average accuracy and IRT rankings on the whole test set compared to the rankings of the same metric on a smaller test set. Our first experiment examines the stability of existing items and subjects, while the second investigates the stability of new evaluation data using sampling strategies. Figure 3. We compare each IRT and linear model on how well they can predict subject responses. We focus on ROC-AUC since response is an imbalanced prediction. Most subjects are correct. Under that metric, all IRT models improve over the best linear model, and the strongest linear model ablation only uses IRT features. That textual features are predictive in the LM suggests that they could improve future models. Section 4.3.1. IRT rankings have better reliability. Rankings should be reliable within the same dataset, e.g. on the dev set, and also generalized to similar datasets, e.g. within a test dataset. To test the first, we measure the ranking stability of mutually exclusive samples of the development data. To test the second, we measure the correlation between set samples rankings to test set rankings. Specifically, for a range of sample sizes, we sample two partitions of the data, compute the classical ranking and the IRT ranking from a refit IRT fees model, and then compute Kindle's correlation between the samples for each ranking. In both cases, IRT rankings have higher correlation than classical. Since the benefit is strongest at low sample sizes, IRT can improve the reliability of small-scale evaluations. The second experiment examines ranking generalization. IRT yields more reliable measures of subject skill, implying a greater consistency in subject rankings across evaluation settings. Figure 4 compares the development set sample ranking computed above to rankings obtained using subjects' test set responses with the same IRT model. Across all sample sizes, subjects' IRT ability estimated on the development set correlates well with testability. Crucially, this is better than the corresponding classical metrics like accuracy, supporting our original motivation for using IRT. Section 4.4. IRT improves cold start reliability. IRT can also guide the construction of tests. Just as IRT practitioners prepare tests for humans, we too construct tests for machines. In educational testing, collecting responses from humans is expensive. Likewise, although questions are cheap in search-based QA tasks, annotating answers is expensive. Likewise, grading machine dialogue responses is expensive, and IRT can help. To emulate this setting, we use computerized adaptive testing to iteratively select squad items to annotate. As in tests preparation for humans, we use existing annotations to infer item parameters and iteratively infer the ability of new subjects. This experiment splits in subjects into a training group and a testing group. The training group represents subjects for which we have full item predictions and annotations. The testing group represents a new group of subjects that we need to rank. To efficiently rank, we should iteratively choose items to annotate that yield the most information about the ranking if all the data were annotated. This experiment compares how well several item selection strategies work. For each selection method, we 1. Choose a sample size, 2. Sample from the development set, and 3. Compute the ranking of subjects, and 4. Compute Kindle's rank correlation. Which item selection strategies should we compare? As a baseline, we use naive random sampling. Like prior work, we compare the selecting items with the highest difficulty and the highest discriminability, as well as the sum of the two. We propose that items should be selected according to their Fisher information content, as derived by Lord et al., 1968. Intuitively, if we do not yet know the true skill theta j, we should pick items whose expected response are most uncertain. Our uncertainty, entropy, is maximized when the likelihood of correct response, Pij, is the same as the likelihood of an incorrect response, 1 minus Pij, which corresponds to the maximum value of the information content. It is also sensible this value increases as discriminability increases. To To infer the maximally informative items, we estimate the ability theta j of each subject using the currently selected items, use the ability to compute the information of each yet-to-be annotated item for each subject, and then aggregate the informativeness by item. This approach is similar to uncertainty sampling and reduces to it for the IRT base model. We initially seed with 25 discriminative questions. Like computerized adaptive testing, Figure 5 shows that at lower sample sizes, 3 of the IRT sampling methods are better than random sampling. Difficulty does worse. The other IRT methods have comparable correlation. Thus, by using IRT, DAD can both improve rankings and guide annotation. Figure 4. Compared to the final ranking over a large test set, how well does a small test set correlate? The left shows correlation between mutually exclusive development set samples and the right between development samples and the full test set. In both experiments, Payne's ranking systems by IRT ability is more stable across all sample sizes than mean accuracy and thus more reliable. Bands show 95% confidence intervals of rank correlations across 10 trials per sample size. Figure 5. Suppose we need to cold start and collect annotations for a new subject. What order would most rapidly increase correlation to the full test data? As we expect, the correlations eventually converge, but with little data, IRT has better correlation than other methods. We suspect that the IRT using information content underperforms early if the subject ability is unstable. Section 5. Qualitative insights on leaderboards. DAD also helps qualitative analysis of items and subjects. First, IRT identifies overfitting and generalizes partitioning datasets by difficulty. Then we show that, like in educational testing, IRT identifies good and bad items. Figure 6. We partition evaluation data by IRT difficulty and discriminability with accuracy in each quartile. Most improvements in high accuracy systems come from getting high difficulty questions right. Items with low discriminability, and thus prone to annotation errors, are difficult for all subjects except the overfit ARGS-BERT model. We include top-performing squad subjects, several hallmark subjects, and a pair from the bottom of the leaderboard. Section 5.1, Guiding Analysis with IRT. Several works curate easy and hard QA subsets based on how many models answer correctly, or heuristics. IRT can create similar subsets using IRT fees, the best 1D model. Difficulty finds where subjects may improve, while discriminability and feasibility can surface items that may be invalid. For example, one low feasibility question asks, what are 2 examples of types of Turing machines? 1, the answer omits 5 types, and 2, span-based evaluation precludes selecting non-contiguous types. After excluding items with negative discriminability, they are likely erroneous, we sort items into bins. We break both difficulty and discriminability into 4 bins, taking the 25th, 50th, and 75th percentiles, creating 8 total bins. Then we select a representative set of squad subjects with their exact match. Let's examine a feasible item with positive difficulty and discriminability, like what reform was attempted following the Nice Treaty. In this case, the annotator span is too long, resulting in almost no correct answers and a low fuzzy match. In contrast, one highly discriminative question succeeds because there are 2 plausible guesses to who did the Normans team up with in Anatolia. While both the Armenian state and Turkish forces are superficially plausible answers, only Turkish forces is actually correct. Nonetheless, some models are fooled. Using IRT to guide subject analysis is helpful. Next, we test how efficient it is in identifying annotation error. To test if IRT can identify annotation error, we inspect 60 squad development test items. We select 10 items from each of these groups, the most negative discriminability nearest to 0, the highest discriminability, the least difficult, the most difficult, and IRT model errors. For each, we annotate whether the item was correct, yet flawed in some way, or simply wrong. Inter-annotator agreement between 3 authors on this 3-way annotation with Krippendorf's alpha is 3.44. Despite only modest agreement, just as in the development of education tests, negative discriminability is predictive of bad items. When discriminability is negative, then the probability of getting the answer right is higher when ability is lower, which is undesirable. Kin consistently loses to BERT. This could identify bad items in evaluation test sets for removal. Section 6, Related Work. DAD draws together 2 primary threads. We use IRT to understand datasets, which has been applied to other NLP tasks, and applied to improving leaderboards. Finally, we explore how the insights of IRT can improve not just the analysis of test sets, but to improve the construction of test sets. IRT is gaining traction in machine learning research, where automated metrics can be misleading, machine translation, and chatbot evaluation. Concurrent with our work, Vania et al. Compare NLP test sets with IRT. Closest to our work in NLP is Otani et al., who rank machine translation subjects and compute correlations with gold scores. Similarly, Martinez-Plumed and Hernandez-Oralo use IRT on non-language AI video game benchmarks. Just as we use IRT to identify difficult or easy items, Lalor et al. Create challenge sets for textual entailment. We test IRT as a way to guide annotation, but it can also train NLP models. For example, deep models learn easy examples faster and maintain test accuracy when training data are downsampled with IRT. Improving leaderboards. The rise of leaderboards in NLP has encouraged critical thought into improving them, evaluation more broadly, and thoughtful consideration of their influence on the direction of research. DAD primarily aims to use IRT to make leaderboard yardsticks more reliable, interpretable, and part of curating the benchmark itself. In line with our reliability goal, just as statistical tests should appear in publications, they should be freebies for leaderboard participants. Alternatively, Ho et al. Posit that leaderboards automatically extracted from publication. How to aggregate multitask benchmarks and multi-metric benchmarks is an open question which, although we do not address, is one use for IRT. This work implicitly argues that leaderboards should be continuously updated. As a static leaderboard ages, the tasks overfit, which, although mitigable, is best solved by continually collecting new data. Ideally, new data should challenge models through adversarial collection and related methods. However, if making an easy leaderboard more difficult is possible, the leaderboard has outlived its helpfulness and should be retired. Part of our work centers on alternative task efficacy rankings, but this naively assumes that task efficacy is the sole use of leaderboards. Indeed, focusing solely on these factors can mislead the public and may not reflect human language capabilities. Leaderboards are also well positioned to provide incentive structures for participants to prioritize fairness and efficiency, or incorporate testing of specific capabilities. To support work like ours in these aims, leaderboards should accept runnable models rather than static prediction. Active learning. Beyond IRT, the analysis of training dynamics and active learning is helpful for actively sampling specific items or identifying low-quality items. For example, Swayam-Depita et al. And Pleiss et al. Propose alternative training dynamics-based methods for identifying difficult items as well as annotation errors. Even closer to our goals, Raman et al. Use active learning to build a test collection. Explicitly measuring how effectively samples separate the best subject from the rest allows test set curators to focus on the bubble, prioritizing examples most likely to reveal interesting distinctions between submitted systems. Alternate formulations. The IRT is an example of convergent evolution of models that predict subject action given an item. Ideal point models consider how a legislator subject will vote on a bill item and use a similar formulation. The venerable ELO model and modern extensions predict whether a player subject will defeat an opponent item with, again, a similar mathematical model. IRT models can also be formulated as nonlinear mixed models, which allows for comparisons between IRT models and other mixed effects models under a consistent framework. As we discuss further in the next section, DAD's application of IRT can further be improved by adopting interpretable extensions of these models. This paper advocates incorporating decades of research in crafting education tests to improve how we evaluate the capabilities of NLP models. We propose and validate an alternate IRT ranking method for leaderboard evaluations, show it can guide annotation, detect annotation error, and naturally partition evaluation data. Just as educators moved from classical testing to IRT, the NLP community should consider future evaluations with IRT. Section 7.1, Limitations. Although there is much to gain through IRT evaluation, there are limitations which make it hard to operationalize. First, it requires access to item-level responses for all examples for all subjects, which are often only available to organizers. Second, Urbano notes that sampling mutually exclusive subsets has drawbacks. Samples are not entirely independent. Lastly, our work is a proof of concept using Squad 2.0 as a testbed, and our results may not generalize. Section 8, Future Work. We see a few directions for future work. First, this paper is intended to validate IRT and its usefulness as an active part of the leaderboard lifecycle. Second, our IRT models do not incorporate the item content when predicting responses, but in principle could. Bayesian models with metadata and ideal point models from political science that incorporate bills and speeches do exactly this. Analogously, IRT for leaderboards can and should incorporate text from passages, questions, and answers to better model what makes questions difficult. Such a model can also predict what characteristics would create discriminating or difficult items. Lastly, multidimensional IRT models to evaluate multiple skills could aid multitask or multi-metric leaderboards like MRQA and Dynaboard. Thank you for making it this far, where we have gone from dusk to twilight. Let me know if you find these read-throughs helpful. I will continue doing so if I get positive feedback. Links to the code and the full paper are in the description.